These are notes and examples for AP Calculus AB from section 1.4. This is what we'll be doing in class. If you are looking for the 1.4 intro video, this is not it. Go back and look for the video labeled intro video for 1.4. All right, so for examples 1 through 2, we're going to find where the function is discontinuous, and we're going to try to classify that discontinuity as removable, a jump, or due to a vertical asymptote. So taking a look here at number 1, we can see that we've got a denominator, a rational denominator, so we definitely have the potential here for a vertical asymptote or possibly a removable discontinuity, also known as a hole. So what I'm going to do is I'm going to try to find that removable discontinuity or vertical asymptote. I'm going to do this by factoring. So the top factors is x plus 1 times x minus 1, and the denominator is, of course, just x minus 1. And so, of course, the x minus 1's cancel out here, and anytime you cancel out a factor from the top and the bottom out of a rational function like this, you end up with what we call a hole or a removable discontinuity. So this function is discontinuous at x is equal to 1, and it is a removable discontinuity. All right, let's take a look at number 2. Of course, this is a piecewise graph, and so what I'm going to do is I'm just going to kind of analyze both pieces and just kind of think about those, and then we'll talk about where they join. So if you look at the top piece right here, 4x minus 1, that's just a regular old line, right? So a line in and of itself is going to always be continuous, right? And then the second piece down here on the bottom, x squared plus 1, that is just a parabola. And a parabola, again, is always continuous. So the only possible spot where we might have a point of discontinuity is where these two functions are supposed to join together. So I'm going to analyze it from this perspective here. I'm going to say the limit as x approaches 0 from the left of h of x perhaps equals, hopefully equals, the limit as x approaches 0 from the right of h of x. So from the left would be the line. This is from the left right here. So I'm going to put limit as x goes to 0 from the left, and that would be 4x minus 1, possibly equal to the limit as x approaches 0 from the right, and then of course from the right would be the parabola. So that's x squared plus 1. So as we've talked about before, anytime you're trying to evaluate a limit, possibly the best way is just direct substitution, and that's the case here. So if I evaluate the first limit using direct substitution, I end up with 0 minus 1, or just negative 1, and the one on the right, I end up with 0 plus 1, of course that's 1, and of course those two are not equal to each other. And so we've got different behavior from the left and the right, and so we do have a discontinuity at x is equal to 0, and it is a jump discontinuity. We can see that because we've got the different behavior from the left and the right. So from the left we're going to be approaching negative 1, and from the right we're going to be approaching positive 1, so it's going to look maybe something like this. Okay, so there's your jump discontinuity. All right, moving on to number 3. Number 3 says, if f of x is not continuous at x is equal to 2, which of the following must be true? These types of questions are always a little on the tricky side. Let's kind of go through piece by piece. I'm going to approach it from types of discontinuities. So in A, it says the limit as x approaches 2 from the left of f of x does not equal the limit as x approaches 2 from the right of f of x. This would be describing a jump discontinuity. So, if f of x is not continuous, does it have to be a jump discontinuity? The answer is no. So I'm going to, we kind of understand what that's saying. It looks like maybe that's not it, but we'll maybe come back around to it and we'll see. For now, let's kind of exit off the list. Part B, or answer B, f of x is not defined at x equals 2. Let's think about what kind of discontinuities that would be. F of x is not defined. So this could be a vertical asymptote, or it really could just be one of those holes, or the removable discontinuity. So again, it really doesn't have to be one of those. So I don't know that B is the answer too. I mean, we can come back around to it if we want, but it looks like maybe the answer is C. Let's think about this. C says f of 2 does not equal the limit as x approaches 2 of f of x. I think this is going to be our answer. This is the most general thing here because f of 2 not equaling the limit as x approaches 2. This could be some kind of a jump. This could be a vertical asymptote because this limit right here could be, infinity or dne. And then f of 2 could be a whole, which then, perhaps wouldn't equal the limit as x approaches 2. C is the most general way to put this, so I think we're looking at probably answer C for number 3. All right, looking at number 4. Number 4 is definitely a classic question, something you commonly would have seen on an AP test in the past. So let's focus in on this one a little bit here. It says g of x equals this piecewise function. Find the value of a so that g of x is continuous for all x. Okay, so a, of course, I think we're probably pretty familiar with this. Whenever we use a letter at the start of the alphabet, it typically refers to a constant, and a letter at the end of the alphabet typically refers to a variable. So a is a constant, so we'll treat it as such. So we're supposed to find a so that this function g of x is continuous for all x. So we've got, of course, the top piece here is a cubic. The bottom piece is a line. We want to make sure these things join up, and the value of a apparently is going to make a difference as to whether they join up or not. So whenever you're asked about continuity, the thing we want to do, of course, is we want to use our limits. And so we're going to say the limit as x approaches -2 from the left of g of x equals the limit as x approaches 2 from the right, or -2, sorry, of g of x equals g of -2. So the left piece would be the line. I'm looking at this less than -2. That tells me that it's the line. So we are going to write limit as x approaches -2 from the left of -3/4 x minus 2 equals, from the right would just be the cubic, limit as x approaches -2 from the right, of ax cubed plus 4. And then g of -2 is taken care of with that cubic piece, right, because it's got the or equal to on it. So I don't have to write that again. Just know that it's contained within that cubic. All right, so the best way to evaluate a limit often is just to plug in the value, just direct substitution. So let's give that a try. When I do that with that first piece with the line there, if I plug in a -2, it looks like I'm going to get 3/2 minus 2 equals, I'm going to try the direct substitution over here as well, and it's going to work just fine. -2 cubed is -8, so it's going to be -8a plus 4. I'm just going to try to solve for a now. So 3/2 minus 2 is -1/2. And I'll continue on up here. I'll just subtract 4 from both sides. That's going to be -9/2 is equal to -8a. Divided by -8, I think we come up with 9/16 is equal to a. All right, so who would have guessed, right? Who would have thought that that would be the value for a that would make this continuous? Really, the only way to do this for sure is to do the process we just did. All right, before we switch gears a little bit, we're going to look at number 5. Number 5, again, gives us a piecewise function, but it says show that. So that means the thing you're supposed to show is probably already true. We're just going to prove that h of x is continuous for all x. So like before, anytime you're asked to prove continuity or show continuity or find something to make something continuous, we're going to use that limit statement. So I'll abbreviate this just a little bit. So the limit as x approaches 4 from the left, and from the left would be this line down here. So it'd be 1/2 x minus 48 is possibly equal to the limit as x approaches 4 from the right of -3x squared plus 2. And of course, that's equal to h of 4. We already know that h of 4 is contained within that line because of the or equal to on that inequality. So like we've been doing, let's do a direct substitution. It's been working out pretty great. So when I plug in the 4 for the x, I'm going to get 2 minus 48, that's -46, possibly equal to, over here when I try the same thing, I get look at that. We plug in the 4, that's 16 times negative 3 is negative 48 plus 2. So negative 46, of course, does equal negative 46. Therefore, we have proved that this function actually is continuous. Our next section here is just a brief treatment of some typical functions and where they are or aren't continuous. So a polynomial is going to be continuous for all x. So those are always pretty handy. We know that they'll always be continuous for all x, and so usually those are pretty easy to handle. Rational functions are going to be continuous for all x except for we want to look out for wholes, again also known as removable discontinuities, also vertical asymptotes. So rational functions would be things like x plus 2 over x squared minus 9 or something like that. Those are rational functions. Radical functions, again, those are going to be continuous over their whole domain, but obviously we'd be restricted to places where we're doing the square roots of positive numbers, so we'd want to look out for square roots of negative numbers. That's going to cause, of course, the graph to not exist, therefore wouldn't be continuous there. And then trig functions, we know, of course, that sine and cosine, those are continuous for all x, but also all the other ones, secant, cosecant, tangent, and cotangent, those all have vertical asymptotes. Would obviously have places of discontinuity at those vertical asymptotes. So again, not a real critical piece there. I just want to kind of spell out how these functions behave and what we want to look out for. Polynomials being the easiest, and then the other ones are going to have some things we've got to deal with potentially. Our final topic for this section is the intermediate value theorem. The intermediate value theorem is spelled out right here. We'll try to unpack it a little bit differently, but I'll read it to you. You can listen or read along with me. It says if f is continuous on the closed interval ab, f of a does not equal f of b, k is some number between f of a and f of b, then there is at least one number c on the interval such that f of c equals k. Of course, this is very difficult just to unpack, just reading the words. I think probably a graph is the best way to go. So that's what I'm going to try to do for you. So I'm going to, let's go ahead and look at just an xy axis system here, and let's get this graph on here. So here is my x, my y axis. We're told that we have this interval from a to b. So I'm going to go ahead and put that interval on here. It's just going to be a little random. So I'm going to say, a is right here, b is right there, whatever. And we're told that f of a cannot equal f of b. So that means that the y values there are not equal to each other. So I'm just going to say that f of a is right down here, and maybe f of b is up here somewhere. There we go. And then k is some number in between those. And so, k would then fall somewhere between, so here's basically f of b, here's f of a. So k would have to fall somewhere in between here. We don't know exactly where, but we just know that this number that perhaps we're going to be finding is between f of a and f of b. Okay, so this, of course, it's mentioned at the start here that this only works if f is continuous. Let's talk about what this means. So if f of x is continuous, essentially what the mean value, the intermediate value theorem is saying is that in order for me to progress from f of a to f of b in a continuous pattern, I've got to hit all the points in between. I can't skip any of the y values. So like all these y values in here, I'm going to have to hit all of them in order to go from a to b. I'm going to have to hit all of them at least one time. And so that's really all the intermediate value theorem is saying. Of course, I could skip some if I did this. I'd be skipping a lot of them. But then in a situation like that, of course, we don't have a continuous function, and so it doesn't really apply. So again, the intermediate value theorem basically is the in-between value theorem. In order to go from one y value to another, you've got to hit all the points in between as long as the function we're dealing with is continuous. And so this number we're looking at here, f of c equals k, would just be somewhere in the middle. Maybe it's here, maybe it's here. It would depend on the specific numbers that we're dealing with, of course. So we're going to do a couple of examples with this mean value theorem. The first one is example A. It says, use the graph of f of x and the IVT, also known as the intermediate value theorem, to prove that the function f of x has an x-intercept on the interval 0 to 3. So in these situations, don't forget to acknowledge that f of x is continuous. And of course, we do know that it is continuous because it's a polynomial. All right, so let's think about this. X-intercept, think about what that is. That is a place where the graph of f of x crosses the x-axis. So, here's the x-axis right here. That means that the graph of f of x, goes through, say maybe like right there. That would be an example of an x-intercept. So let's think about what we would have to prove in order to, prove that that actually exists. What would we have to show? I want you to think it over. Maybe pause the video here and do some thinking, do some writing, and see if you can come up with it. I'm going to go ahead and tell you what it is. Essentially this, at the x-intercept, the y value is 0. So, based on the intermediate value theorem, for me to prove that y equals 0, I need to prove that somewhere on the interval y is negative, and then I need to prove that somewhere else on the interval y is positive. So if I can prove that y is negative somewhere and y is positive somewhere, then I'd have to go through 0, wouldn't I? Because 0 divides the negatives and the positives up. So that's what I'm going to shoot for here. I'm going to erase my graph because that's not really a graph of our function. So here goes. I'm going to just try some test values and see what happens. I'm going to use the endpoints of the interval. I think we'll find that those work. So if I evaluate f of 0, I end up with positive 8. And if I evaluate f of 3, which is just the other endpoint, I don't have to use those. I could use other values, but I'm using these. I end up with 9 minus 18, which is negative 9 plus 8. I get negative 1. So I think I've set myself up here pretty good. I have found that f of 0 is positive, and I found that f of 3 is negative. So what I can then say is, because f of x is continuous, and f of 0 is bigger than 0, and f of 3 is smaller than 0, f of x must equal 0 somewhere on the interval from 0 to 3. Therefore, we'd have an x-intercept. So that's the intermediate value theorem. All it's saying is to go from one y value to a next, I've got to hit all the y values in between. Letter B here is another really great example. It says f of x is polynomial. Of course, that's significant. What does that mean? It means that f of x is continuous. It's important for what we're going to do here. Got a table below. Selected values of f of x are given. What is the minimum number of times that f of x is equal to 2? Justify your answer. So again, I suggest that you try this on your own. I'll just go ahead and proceed with the answer here in a second. But feel free to pause the video and try this by yourself. So in order to prove that f of x equals 2, I essentially need to show that somewhere f of x is below 2, and then somewhere else f of x is above 2. So I'm going to start right here on my table on the far left edge. I can see right here that the y value is less than 2. And then immediately, when I move to the right, the y value is now bigger than 2. So that would be one time. I had to go from 0 to 3, I've got to go through 2. Well, from y value of 3, I go to a y value of 8, so I don't think that I have to have hit a value of 2 in there. But to go from 8 to 1, I have to hit the y value of 2 again, so there's a second time. From 1 to negative 2, as I proceed, I don't have to go through 2 to get there, but to go from negative 2 to 7, I've got to go through a y value of 2, so there's time number 3. And finally, to go from 7 to 10, I don't have to go through 2. So I think we'd settle on 3 times. So here's how I would answer this. First of all, I'd just say 3 times. And then I would say something along the lines of f of 2 is less than 2, f of 4 is bigger than 2, f of 9 is less than 2, and f of 13 is bigger than 2. Because f of x is continuous, f of x would have to equal 2 at least 3 times. If you want to include the, just the IVT, just to say I'm using the IVT, I think that's a great way to go. As long as you're using the idea of the IVT, if you're clearly spelling it out and using good reasoning, you don't actually have to name it. But it might not be a bad idea to name it. Finally, let's take a look at example C. Example C, of course, uses a graph. And again, I suggest pausing the video, trying this on your own, watching the video to see how we did. It says 3 values of g of x are shown below. What is the minimum number of x-intercepts for g of x. So the temptation here is to say 1, right? People will just connect the dots. People will connect the dots and say, something like this, so there has to be at least 1. The truth of the matter is we really can't answer this question. The reason why we can't answer this question is to use the idea of the intermediate value theorem, which is what is tempting to use here. We have to have continuity. We are not told that g of x is continuous. We're not told at all. Is g of x continuous? Well, if it is, then we'd get one answer, and if it's not, we'd potentially get a whole different answer. So because g of x is not continuous, or excuse me, not that it's not continuous, we just don't know, we can't answer the question. The IVT does not apply. Does not apply here. So kind of a trick question. We just can't answer it, really. We can't say yes or no either way. Just can't answer it. Okay, so the IVT is what we call an existence theorem. Kind of challenging because it doesn't really give us an answer. It just tells us that an answer exists. Sometimes we actually can go on to find the answer. We will look at a couple of others. See the mean value theorem, Rolle's theorem. These are important and can definitely be assessed in a number of ways. So make sure you're familiar with them and familiar with how they work, not just calculating values, but what they actually mean, the concept. So I hope this worked for you. See you in class soon.